Welcome back, everybody. Today's lesson is out of Chapter 3, Section 1. We will be discussing functions today. And so as we discuss functions, there's multiple different items that we're going to be taking a look at. You can see those on screen. I'm not going to read through all of those. But today's lesson is a critical lesson because functions form a large part of what we do in algebra and what we do later on in other mathematics. So overall, let's start with the definition of just a relation. A relation is what we call a correspondence between two sets. So what does that mean, a correspondence? It means we're putting two sets together, two numbers together, two items together. So we see it over here in example, or table 1 rather, on the left of the screen. We have time in seconds, okay, and we also have height in meters. That's two sets. We have time and we have height. So this entire table represents a relation. In figure 2, what we have on the x-axis is we have time. On the y-axis, we have height. Again, two different components. So if we have two different items, two different components, and they're together, then we say that we have a relation. In figure 3, we also have time, we also have height, and so that is another way that we can describe a relation. We can go ahead and take a look at these three different items, ways to describe two sets. So what do we have overall? We have a table, we have a graph, and notice on this third set, and sometimes they look rather organic, and these look a little bit more like beans of some sort. They could just be ovals. Later on, we'll see them as rectangles. But the main thing is that we have a starting point and then an arrow that takes us over to an ending point. So since we have a starting point and we're being told how to go to the next spot, then we say that we have a map. So we have tables, graphs, and maps that are different ways that we can describe these relations. So another way that we take a look at describing relations is verbal descriptions. And so in this one, let's take a look at what we have, and then we'll do some other items with it as well. So this one's just out of the textbook here. Verbal description of a relation is given below. So the price of first-class U.S. postage stamps has changed over the years. To mail a letter in 2015 cost 49 cents. 2016 cost 49 cents for part of the year, 47 cents for the rest of the year. In 2017, it cost 47 cents for part of the year and 49 cents for the rest of the year. And in 2018, it cost 49 cents for part of the year and 50 cents for the rest of the year. So let's use year as the input and price as the output. So if we think about this, so year as input, oops, intended to have the highlighter. So year as input, price as output. Those are the things that we're looking at. So we have two different components. We have input, output, we have year, we have price. As we take a look at these, letter A says what is the domain and the range of the relation. So when we take a look at our domain is all the things that we're allowed to use as input. So in this case, our year is going to be our input. And so what is our years, or what are the years? In this case, our years, let's see, we got 2015, we have 2017, we also have, let's see, 2018. Did I skip 2016? Yes, I did in the second line there. It seemed likely if we're going from 215 to 218, but also should have had all the numbers in there. So we got 2015, 2016, 2017, 2018. Those are all the items that I have in my domain. Notice I also wrote those in these curly brackets here. Typically when we're dealing with sets of numbers or lists of numbers, we go ahead and write those in those curly braces. So that is my domain, all the things I have for my inputs. My range is what we have for our outputs. And our outputs in this case, we were told are going to be our prices. So what are the prices that we have? Let's see, we've got a 49 cents, we've got another 49, we've got a 47, another 47, another 49, another 49, and then we've got a 50. Typically, when we write these, we don't list the repeats. So I had several 49s in there, several 47s. I'm not going to list those more than once. When we list things out, what we're doing is we're listing the things that are used, the things that are possible. So I do not have to repeat anything. Generally, and although it's not required, generally we do like we did the years, we also put these in numerical order. So I've got 49, 47, and 50 cents. So I'm going to write the 47 cents first, then the 49 cents, and then the 50 cents. And we could put the zeros in front if we want. Also put the dollar symbol. So that we say, okay, we got 47 cents, 49 cents, 50 cents. So that is the domain and the range of these relations. So now we can go ahead and we can take a look at the other components. Let's write this relation as a set of ordered pairs. Let's do it as a map. And then let's also write it as a graph. Okay? So the three different ways that we typically write these items. So I'm going to pull this off the side here. And we're going to say, okay, so letter B, write this as a set of ordered pairs. So in 2015, what did we have? Okay, so again, because we're listing things, I'm going to go ahead and write these inside my curly braces. So I had 2015 as my input, and then I had 49 cents as an output. So that is a pair. That's something that took place, and that's the only thing we had. Then in 2016, let me go ahead and eliminate some of the stuff up here. In 2016, we had 49 cents and we had 47 cents. We got to list both of those. So let's see. So we've got 2016, we had 49 cents. And also in 2016, we had 47 cents. So that takes care of all of 2016. Then in 2017, let's see here. So 2017 we had 47 cents and 49 cents. So we'll go ahead and list those. So in 2017, we had 47 cents. Also in 2017, we had 49 cents. And let's see, then in 2018, we had 49 cents for part of the year and 50 cents for the rest of the year. So let's see, 2018, move this over here at 49 cents. And also in 2018, we had 50 cents. And since that's the last number, the last set of order pairs, I'm going to close that off with a set of parentheses. So in part B, what we did is we took all of these values and we put them as ordered pairs. So what do we mean by ordered pairs? As we take a look at this component, every single group here is a list of two. I have the year, okay, so we have all of the years listed in here, followed by all of the prices, okay? So in this case, if I do it this way, I'll go ahead and write this down here, we have our year, and then the price. Our year was our inputs, our price was our outputs, our inputs, again, this is what we call the domain, and our output is what we call our range. So tell me what year we're interested in, and I can look through my table and I can say, well, what were the price or prices during that particular year? The other thing we can do, okay, so that's letter B. Part C says express each relation as a mapping. So if we do a map on this one, let's see what we can do. So I'm going to take a look at just part B here. I'm going to put C off to the side here. So this was ordered pairs for part B. And we're going to do the mapping over here in part C. So in the mapping, what we do is we have this organic approach as far as what are the domains that we're using. So our domains, we had 2015, 2016, 2017, 2018. Then we have, okay, what are the prices that we had? And the prices, if we go back over here to our domain and range, okay, for our range we had 47 cents, 49 cents, and 50 cents. So we're going to write those over here. So we had 47 cents, we had 49 cents, and we had 50 cents. Now, oftentimes these are drawn either in ovals or some kind of organic shape, or they can also be in rectangles, depends on how the author wants to go ahead and write those. The mapping then, if we go back to our ordered pairs, we can do our mapping from our ordered pairs. Our first ordered pair was 2015 mapped to 49 cents. So I can draw an arrow then from 2015 over here to 49 cents. And say, okay, so what's my map? If I'm at 2015, I can go to 49 cents. 2016, I'm just going to read in order here. 2016 went to 49 cents. Whoops. And let's see, 2016 also went to 47 cents. 2017 went to 47 cents. 2017 also went to 49 cents. 2018 to 49 cents. And 2018 also went to 50 cents. So given any particular year, then we can follow the arrows to see where it went. So in 2015, it only had one arrow going off of it. It was only 49 cents. It was 49 cents the entire year. In 2016, however, we had two prices. For part of the year, it was 47 cents. Part of the year was 49 cents. Same thing with 2017, 2018, with different costs throughout the different years. And so that is what we have, a map. So the ordered pairs and the map tell us the same data, they're just described differently. Part D then is asking us to go ahead and make a graph of these items. So this is where we're going to draw an XY plane. And whenever we do this, so let me get my screen to stop here, our domain is always going to end up being on our x-axis, or horizontal axis, and our range will always end up being on our y-axis, or vertical axis. So we're going to have years on our x-axis, and we're going to end up with prices on our y-axis. So let's see, so we're going to do 2015, 2016, 2017. Just need to expand this out just a little bit longer here. And then we've got 2018. Then our cents here, so I'm going to put a little break in the axis there. So let's call this 47 cents, 48 cents, 49 cents, and then of course 50 cents. And then what we will do is we'll just go ahead and plot points. So I can go back to either then, I can go back to my ordered pairs, or I can take a look at my mapping. And so since my map is right close to my graph, I'm just going to take a look at the map then. 2015, I'm at 49 cents. So 2015, go up to 49 cents. We're going to place a dot. 2016, we have two prices. We have 47 cents and 49 cents. 2016, 47 cents and 49 cents. 2017, we have 47 and 49 also. So there's 47, 49 again. And then in 18, we had 49 and 50. So we've got 49 cents and then 50 cents. So overall, what we can see then with this component is we do have three different ways that we can go ahead and visually describe our data. So we had our ordered pairs, we had our mapping, and then we also had our graphs. So different ways to describe the exact same sort of material. What we can do after that is, once we figure out how to just describe a relation, so that's what we have a relation. We define a function then as a specific type of relation. So let's come back over here to our notes. So by definition, a function, let x and y be two non-empty sets. So what it just means to be non-empty is that x has to have something that we're talking about, and y has to have something that we're talking about. So hey, do x and y form a function? Well, x is the amount of time, and y is, and we don't describe y. We don't have anything for y. Well, it wouldn't make any sense for us. So what we have to have is we have to have two sets that have things in them. Okay? And a function then, the formal definition of a function, is a relation that associates each element of x to exactly one element of y. And the exactly one element of y is the thing that makes it a function. So for every x value, there can only be one particular y value. So when we take a look at our ordered pairs here for our last example with our years and our price, For every year, I can only have one price. That would be a definition of a function. So when I take a look at this first item here, 2015 is 49 cents, that's okay. I have 2015, I have one price associated with it. Where I run into problems with this being a function is in 2016, I have two prices. So I have one input, but I have two outputs. Remember, our formal definition for a function here is that for every element of x, there's exactly one element of y. And in this particular case, I have an x value of 2016, but I have two y values. I have one input, but I have two outputs. I have the same dilemma here in 2017, and I have the same dilemma here in 2018. So all it takes is one of those x values, one of those years, to have two different prices, or three different prices, or four different prices, or more than one price. And as soon as we have more than one, then we're still a relation, but we're not considered a function. So when we take a look at ordered pairs, one of the things that we key in on is take a look at the first value. If the first value is repeated, like we have 2016 listed twice, if it has two different y values, then it's no longer a function. When we take a look at the mapping notation, with our maps, if I only have one arrow, so like in 2015, I only have one arrow that comes off of that, that's okay. In 2016, I have one arrow and then a second arrow. Because I have two items that come off of that and they go different locations, then I'm no longer a function. And I have the same dilemma here with 2017, same dilemma with 2018. If we take a look at a graph, one of the things that we typically employ is what is called the vertical line test. So if I take a vertical line here, the vertical lines are when x equals a particular value. So when x is 2015, how many places does this vertical line get associated with? Well, in this case, at 2015, it's associated with only one value. It's associated with 49 cents. That's okay. That's what we want. If I take another vertical line here, when x is 16, 2016, I have two different values. So I have more than one value associated with my x. So since I have more than one y value associated with my x value, it can still be a relation. The relations are just ordered pairs, which is fine. But this is what's not considered a function. Okay? So we have taken a look at a variety of things here, several examples of things that are functions, or excuse me, in this case, we've not seen things that are functions, we've only seen things that are not functions. Let's take a look at some other examples of things that are functions then. So I get a little ahead of myself. Let's zoom out here a little bit so we can see all of this one. So let's take a look at example 2 from our textbook. And we're going to determine whether a relation given by a mapping is a function. So for each relation, state the domain and the range, and then determine whether the relation is a function. So we have two different items here. We want to state the domain and range, and then determine whether the relation is a function. So the first part, we have to list things. The second part, then, is just a yes or no. So part A is going to be figure 8, and we have the relationship shows a correspondence between an item on McDonald's $1, $2, $3 menu and its price. And this is from 2018, so this data is a little older here, but it's still good data to go ahead and take a look at. So as far as our domain here, typically we can abbreviate D for domain. Our domain, is our menu items. So we have a cheeseburger, we have a McChicken, we have the bacon McDouble, we have the triple cheeseburger, and then we have the Happy Meal. Close off our curly braces there. Then for our range, we have, let's see, we have $1, $2, and $3. Okay, much simpler to write that one out than what we had before. Basically, what we have here is our domain is where we start, and our range is where we end. Okay, so our domain were all the menu items, and our range was the price. So that's the first part of what we're looking for. Then we want to see, is this a function? Is it not a function? So if it's a function, then for every item in my domain, there is only one arrow that comes off of it. I can only have one corresponding y value for every x. So for every x, there's exactly one y value. So if I take a look at the cheeseburger, there's only one arrow that comes off of it. If I walk up to the counter and I say I want a cheeseburger, I want to know what they're going to charge me. If they're going to charge me $1, if they're going to charge me $2, they can't on one day say, hey, it's $1 today, and the next customer gets $2, and maybe the next day I'm $2, the other customer is $1. We'd have some issues with that. So with the prices, tell me what the value, the price is for um, every item on the menu. Okay, so the prices can repeat themselves. Okay, we have multiple items be $1. We've got a cheeseburger is $1 and a McChicken's $1. That's okay, and we're still a function. So our bacon McDouble is only $2. Triple cheeseburgers only $3. Half meal is only $3. So one of the things that we see here is that for every menu item, there is only one price that's associated with that particular menu item. So in this case, yes, this is a function. It does satisfy the idea. One of the things to point out then is that my menu items, none of those things can repeat. My pricing items, they can. So for every menu item, I can only have one price, but that same price can be the same for multiple menu items. $1 for a cheeseburger, $1 for a McChicken is okay, but $1 for a cheeseburger and also $2 for another cheeseburger doesn't make any sense. So domains and ranges here, functions for every domain. If there's only one item associated with it, then it can be a function. So we cannot repeat our domain values. We can, however, repeat our range values. So with our next item, we have the correspondence between activity level and daily calories needed for an individual with a basal metabolic rate of 1,975 kilocalories per day. So our domain then is the activity level, and our range, oops, move this down back again, our range then are the daily calories. So I'm not going to write out every single item here as far as what we have, but we go ahead and list those. Actually, I probably should here. It's going to be a little bit lazy. Let's not be lazy. Let's not be sedentary. Okay, so sedentary, then we have light, then we have moderates, and we have intense. Those are all of our activity levels. That's our domain. And our range, or what are the daily calories, the basal metabolic rate for each of these. So we have 2,370, 2,716. We have 3,061, and we have 3,407. So that is our domain and range for part B. And then is this a function or not? Since every item in my domain only has exactly one item associated with it, then we would say yes, this indeed is a function. When we take a look at figure 10 here, this is a kind of a fascinating one. This is the gestation period in days and life expectancy in 5 animal species. And so let's see, we have our domain here. Our domain, we have 122, 201, 284, and 240. Now, one of the things you notice on this one is that one of the previous examples I did was said normally we go ahead and try to write these in numerical order, and what did I just do? I went ahead and put the 284 first and then the 240 second. When even though it's generally acceptable to go ahead and write things in numerical order, it's not a requirement. So I can do it, but I'm not required to do it. And in this case, since I'm writing the list and I have my list already here, I'm going to go ahead and make my numeric list in the same order. So some of this is based off context. And so let's see, my life expectancy in years then, 5, 8, 12, 15, and 20. So listing our domain and our range. Is this third example with a gestation in days and a life expectancy in years? Is this a function? And the issue that I see here is not with 122, 201, or 284, but with 240. With 240, we have life expectancy of 12 years, and we also have a life expectancy of 20 years. So since I have one of these items here that is not limited to a single value as far as my range, then I end up saying, no, this is not a function. It is still a relation. It is still a set of ordered pairs. it is still these things put together, and we can map these, okay, and that's fine. But this is just no longer than a function. Moving on to example 3, we have just a series of ordered pairs in this case. So, and our question here is for each relation, state the domain and the range, and then determine whether the relation is a function. So in example 2, we were given all mapping notations, and we were asked the same thing, state the domain and range, then determine whether or not it's a function. And what we were looking for was the number of arrows coming off an item on the left-hand side. Now we have not the mapping, but we have the ordered pairs, and we're doing the same thing. So for part A, let's see, I want my domain. My domain is all my input values. So I'm going to list my curly braces. And sometimes my curly braces look kind of off, and other times they look really sharp. And so yours might look a little bit happenstance from time to time. And just try to be somewhat consistent through here, but don't beat yourself up if they don't look absolutely ideal, or they don't look quite the way that they look in the textbook or whatnot. But we are trying to indicate that we have these curly braces here. So my domain are all my x values. So all my x values in this first item are 1, 2, 3, and 4. Okay, so that was everything in my range, or my domain rather. And in my range then, those are going to be all of my y values. I got 4, 5, oops, my board's moving a little bit here, 4, 5, 6, and 7. So I can go ahead and write those down here, 4, 5, 6, and 7. So I have my domain, I have my range. Would this be considered a function? Well, for every x, is there only one corresponding y value? For every first item listed, is it only listed once with only one corresponding value? And in this case, yes, it is. 1, as far as a yellow 1 here, gets mapped with only one blue 4. Every yellow 2 only gets mapped to a blue 5. Every yellow 3 gets mapped with a blue 6. Every yellow 4 gets mapped with a blue 7. If I had like 3 getting mapped to 6 and 3 getting mapped to 7, then it would no longer be a function. Take a look at group B. Again, same thing. Let's find our domain and our range. So our domain are all our first values. So I have 1, 2, 3, and 6 in this case. And then for our range, my curly braces there looked fairly sharp, so I was just pleased at that. Every once in a while, you got to celebrate your successes, yes? Okay. So my range, I've got 4, 4. Oh, okay. So my range is repeating, not necessarily a problem. It's just a notation that we only have to list it once when we list our domains. So we got 4, 5, and 10. Okay. So we got 4, 5, and 10. I don't have to list 4, 4, 5, 10, because when we list our domain and range, all we are doing is we're listing all the things that are being used. So it doesn't matter how many times it's being used. If it's being used, and those are things available to us, those are the things that we're listing as far as our range. Now, is this a function? So one of the things I noticed is that my range was repeated. When my range is repeated, not an issue. My dilemma is if my domain is repeated with a different range value. So if I take a look back here at letter B, take a look at all my yellow numbers. Those are all the items that designated as my domain. I've got only 1, 1, only 1, 2, 1, 3, and 1, 6. So each one of those is only going to one corresponding y value. And since that is the case, we can say, yes, this is indeed a function. Taking a look at letter C, we'll do the same thing. We'll list our domain, and we'll list our range. So see, our domain here is -3, -2, 0, 1, and -3. Well, we got a -3 in the beginning, and we got a -3 in the end, don't we? Okay, so that, as far as an item in our domains, that could potentially be our downfall. That could be a dilemma where we're no longer a function. And if we take a look at what they're paired with, -3 at the beginning is paired with 9, -3 in the end is paired with 8. Since they're different things, I already know that on letter C here, this will not be a function. And the dilemma is that my input value of -3 has two different output variables. So that -3 is a domain has 2 items in the range. Now, I still need to list these out, though. So let's see. So I got -3, -2, 0, 1, -3. I don't have to list that twice, so I can stop there. Then my range, let's see, I've got 9, 4, 0, 1, and 8. So I'm just going to list those in order there. 9, 4, 0, 1, 8. As far as when I said the order in which they were listed in the original question. I could also have rewritten this. This would be the same as 0, 1, 4, 8, 9. That would be another way that we could have written our range in this case, because we can put it in numerical order. We do not have to put it in numerical order. Okay? So what we take a look at then is in example 2, we had maps and trying to figure out what's our domain and what's our range. So domain with the first items, range the second items. Domain where our inputs, domains range our outputs. So tell me what you want on the menu. I can tell you what the price is. Tell me what your activity level is, and tell you what your basal metabolic rate is. Tell me the gestation number of days, and tell you what the life expectancy is in years. On example 3, we had ordered pairs. Don't know what they are, we just know they're ordered pairs. So in example A, 1 went to 4, 2 to 5, 3 to 6, and 4 to 7. Okay? And now, let's take a look at a sneak peek at some of the rest of the items in here. Determine whether a function in example 4 and 5, determine whether an equation is a function, not just from the equation. So let me go ahead and move number 6 out of the way here and put a little space between, little space between 4 and 5. So when we take a look at example 4, determine whether the equation y equals 2x minus 5 defines y as a function of x. One thing we can think about then is if I plug something in for x, we're going to multiply by 2. We're going to take that value and subtract 5. Tell me any value for x. If I multiply by 2, I can only tell you one other value. If I multiply, say, 1 by 2, I get 2. I don't get any other number. If I multiply 5 by 2, I get 10. I don't get any other number. Think of any other number you can plug in for x. When we multiply by 2, we only ever get one value back. So with that logic and with that reasoning, we would say, yes, this is indeed going to be a function. If we would take a look at a graph of this, y equals 2x minus 5, it's going to look something of this sort. Okay? And when we do that, if we think about the vertical line test, for every x value, so for this x value, I've got that corresponding y value. For this x value, I've got that corresponding y value. Now let's see, for this x value, I've got this corresponding y value. So in each of these items, it does pass what we call the vertical line test, and so this does end up being then a function. If we take a look at the equation x squared plus y squared equals 1, does that define y as a function of x? What we can do is, unlike the first equation, where it was already solved for y, we need to solve the second equation for y. So if I have x squared plus y squared equals 1, I can move this x squared to the other side by subtracting it. And then in order to figure out what my y value is, I need to take the square root. So when I take the square root, I get y equals plus or minus the square root of negative x squared plus 1. So for every x value that I plug in, okay, so every time that I plug a value in here for x, I'm going to square it, take its opposite, add 1, take the square root, and then I have to consider the positive component of that, and then I'll take its negative component of that, or its initial component, and then its opposite. So for every x I plug in, I end up with 2 different y values. So for that reason, this is not a function. Now, one of the things we might have done, if we go back to x squared plus y squared equals 1, that is the equation for a circle with a radius equal to 1. Okay? And if we take a look at that, when we see the circle, we would say, oh, if I take a look at a vertical line test here, if I take a vertical line test, so when x is over here, I get a y value here and a y value there. Since I get 2 y values, then that would no longer be a function. So we can take a look at it from a equation standpoint. We'd also take a quick look at it from a graphical standpoint and figure out that this is not going to work for us. This is not going to be a function. So far what we've done is we've defined relation, so just a set of ordered pairs, and is in these relations three different ways to write them. We can write them as a table, a set of ordered pairs. We can write them in the mapping notation, so drawing arrows from an x to a y value, from an input to an output, from a domain to a range. We've also seen these graphically. The other thing that we want to take a look at, or one of the other things we want to take a look at, is just finding values of functions. So what if we are already told this is a function, and we just want to know what is the value of the function? So we end up with something called function notation. So for the function f defined by f of x equals 2x squared minus 3x, and it says evaluate. This notation here, f of x equals 2x squared minus 3x, we pronounce this f of x. So this is a function. So this piece here is the name of our function. This is function f. We could have, say, function g, or function a, or function r, or function t. So whatever name that we want to ascribe to that. And then, so that names the function. And then what's in parentheses is what is our input. Okay. So these are all the different values of the domain that we could start with. So I start with a number and say, okay, function f, what are you going to do with this number? Where are you going to send me? And since I know this is a function, I know it's only going to send me to one location. Okay? So for instance, on letter A, we'll say, okay, what function we're going to use? We want to use function f, and we want to say, function f, what are you going to do with 3? And sometimes we call this a function rule. So the rule is we're going to do 2x squared minus 3x. So I'm going to take 2. I'm going to take my input here. I'm going to square the x, so square the 3. I've got minus 3 times, and I'm going to multiply by that 3 also. So what we end up with is we say, okay, function f, take 3, do some stuff with it. So what do we end up with? So this left-hand side is just, we've told function f what our input is and what we want to take place. So this left side is just notation. We don't do anything with that. We just leave it as is. All the work is going to be on the right side here. So we're going to do, this is just order of operations. So 2 times 3 squared. 3 squared is going to be 9. And 3 times 3 is 9 over there. So we got 2 times 9 is 18. And subtract 9. 18 minus 9 is 9. So my function f evaluated at 3 gives me 9. So this would be the same thing as saying I've got the ordered pair 3, 9. Okay? And so 3 was my input, my x value, my domain, or element of my domain, and 9 is my output, my y value, my element of my range. The nice thing about function notation when we start working in algebra is that the input and the output are listed side by side. What is f of 3? Oh, it's 9. If I would write this the other way that we can write notation here is we could have said y equals 2x squared minus 3x, and then say, okay, let's go ahead and substitute. Let's substitute 3 in here for the x values. And at the end, we would have had 3 equals 9. We would have done all this other work on the right-hand side up over here. But at the end, we would have just had y equals 9. Well, that's nice. We get the same answer. But we would not have known just by taking a look at it what our input value was. When we take a look at the function notation, I know exactly my input. My input was 3. I ended up with 9. So let's do a variety of these other items. Okay, so let's take a look at example B. I want a function, and I want x as my input. Then I want to add another function, and I want 3 as the input. Okay, so on this one, let's see what we can come up with. So let's see. I've moved my item out of the way here. So my function originally, f of x, was 2x squared minus 3x. That was my function. So what I have in this notation, I have the function f with x as the input, and then the function f with 3 as the input, and I want to add those two values together. Okay? So what I'm going to first do is I'm going to take a look at this yellow piece, f of x. So take a look at that function rule f, and say, okay, plug x in as the input. Oh, well, I know what that is. That's 2x squared minus, almost put a plus sign there, minus 3x. So that material was f of x. Okay. I'm going to put that in parentheses there. Then I want to add, okay, so that was that add piece. And then I want to go ahead f of 3. So now I'm going to do the f of x function, but I'm going to plug 3 in here for x. That means I'm going to plug 3 in here for x and 3 in there for x. So I've got 2 times 3 squared minus 3 times 3. And let's see, I used that blue for that piece. So there's that component. So we see where we're getting all of these parts and pieces. So overall then, I can go ahead and ignore the um, color coding for the moment and just go ahead and expand this. So that's going to be 2x squared minus 3x plus, so I got 2 times 3 squared. So we just did that, did we not? So on that last example, we had f of 3, and so we ended up with f of 3 was going to be 9. And so we can take a look over here and we say, you know what, I already know what that value is. That's going to be 9 also. Now, if we wanted to, we could expand it out and we could do all the work. But since I already had calculated that, I'm just going to leave that as there. So I end up with 2x squared minus 3x plus 9. Well, what is that? That's f of x plus f of 3. So that would be our answer. Sometimes in mathematics we end up with answers that are going to have variables in them, and we will not end up with these nice, neat little items like, oh, well, this is going to end up being 5, this is going to end up being 12, this is going to be 15. We end up with other algebraic answers, so to speak. We have unknowns in it. Let's do another example. Let's do letter C here. So letter C, I go here with 3 times f of x. So let's see, I went 3 times f of x. Okay. So back up in through here. Okay. So let's see, I went 3 multiplied by, so let me do it this way. I've got 3 multiplied by f of x. Okay, so there's my 3. Now I want to go ahead and write down f of x. Well, what is f of x? By rule, f of x was 2x squared minus 3x. So I have my 3 in both cases. Then I'm doing a substitution. F of x is the same as 2x squared minus 3x, so I substituted that in there. And then I can simplify this. So on the left-hand side, again, my notation just stays the same. That's going to be 3 times f of x. And on the right side, I'm going to do my work. So I'm going to do distributive property here. So 3 times 2x squared is going to be 6x squared. Then I've got or 3 times minus 3x, so 3 sets of minus 3x is minus 9x. And that is going to be our answer for part C, 6x squared minus 9x. Let's do several more of these, okay? Let's see, so part D here, if I write this down, I want f of negative x. And again, f of x, what was our original function? 2x squared minus 3x. So if I want f of negative x, what I want to do then is I want to replace x. Every time I see x, I want to replace it with negative x. So I've got 2. I'm going to put something squared there, minus 3 times something. Well, what's my something? My something here was what I'm replacing x with. In this case, I'm replacing x with negative x. So I have f of negative x equals, and let's see, the square of negative x is x squared, so that's 2x squared, so it'd be negative x times negative x. Okay, so that's x squared, negative turn positive. Then I've got negative 3 times negative x, so that's another positive. So that's going to be 2x squared, 2x squared plus 3x. That is the value of f of negative x. Now let's contrast that then with part E, which is negative of f of x. So notice what happened then on part E here. We're moving our negative from inside the parentheses to outside our parentheses. So when I take a look at this, I'm going to end up with the negative of whatever f of x is. And f of x is this whole thing up here. F of x is 2x squared minus 3x. So notation-wise, the left side stays the same. And now this minus is going to get distributed inside. So I'm going to end up with negative 2x squared and a negative of negative 3x, or the opposite. When you think about that minus sign in the front there, instead of saying negative, we could say that's the opposite of the value. So we have negative 2x squared and the opposite of minus 3x, which is positive 3x. And one thing to note here is that f of negative x and the negative of f of x do not end up as the same thing in this case. Sometimes they might, sometimes they might not. And this is an example where they are indeed actually two different values. But our idea here is that we're substituting in different components. So if we do some more examples here, let's see, that was just letter E. Let's take a look at letter F. We have f of 3x, and again our function rule f said wherever our input is, square it, multiply by 2, and then subtract 3 times its product. Oops. So f of 3x. Okay? So what we're going to do is we're going to plug 3x in for every x value. So we got 2 times the x squared minus 3 times the x. So what I'm going to do is I'm going to replace in these parentheses here, I'm going to replace that with the 3x. The left side, again, nothing more than the notation. So I've got 2 times, let's see, 3x times 3x is 9x squared, and then minus 9x. Oops, forgot my x over here in my notation. So f of 3x is now going to be 18x squared minus 9x. And that will end up being my answer for f of 3x. Where else can we put that 3? Well, on example G, what if we said I want f of x plus 3? So now instead of replacing x with x with 3x, I'm now going to replace it with x plus 3. If I go back to the same pattern as far as highlighting these pieces where they've come from, so every time I have my x, now I'm going to replace the x with what's in the rule. So this position here is my input. So I want to input x plus 3 into my function. So if I take a look at that one, 2 times x plus 3 squared, so that quantity squared, so that means 2 times x plus 3 times x plus 3. Then I have this minus 3, so I can distribute that minus 3 times the x plus 3. So get minus 3x and then minus 9. So left side still notation. Now one thing that some people do on that left side, they'll draw a line over here where all the equal signs are, just to separate the left side from the right side. If that's something that helps, obviously go ahead and use that. If you don't want to write that, you don't not required to write that. It's just one thing visual that sometimes we do to go ahead and assist and help out. So what we can do here is I'm going to leave this 2 on the outside. Then I'm going to FOIL this, use distributive property. So x times x is x squared. First terms. Outside terms, I'm going to get 3x. And do inside terms, so plus 3x. And the last terms are plus 9. Of course, I still have that minus 3x minus 9 that's just going to get written back down. And then let's see, this 3x plus 3x is now 6x. I'm going to distribute this 2, so I get 2x squared. 2 sets of 6x is going to be 12x. 2 sets of 9 is 18. We got minus 3x minus 9. Combining like terms, let's see what we end up with. We got 2x squareds. We have an x, 12x and a minus 3x, so that's a 9x. I have an 18 and a minus 9, and that's a plus 9. So f of x plus 3, as opposed to f of 3 times 3, or f of 3 times x rather, in example G here is 3x squared plus 9x plus 9. One last example in this whole scenario here. So we had our rule for x was f of x was going to be 2x squared minus 3x. So our very last item here, let's call this example h, is going to end up being f of x plus h. And we'll use that x plus h later on and when we get to another example here. But at least we'll start off with this x plus h. Again, the major component is, and the idea of what we're trying to take a look at, is that every time I see x, I'm going to replace it now with x plus h. So I got 2 times something squared minus 3 times something. And what's that something? That something is going to end up being my x plus h. So I got x plus h here and x plus h there. So left side again, nothing more than notation. And then I'm going to end up with 2 times x plus h multiplied by x plus h, because that's the idea of square, minus, and I'm going to distribute that 3 through, minus 3x and minus 3h. On this left side, this is going to stay as is. Does that h look like a b there? That makes it look a little bit more h-like. And so, again, I'm going to leave this 2 on the outside. I'm going to distribute or FOIL. So the first term's x times x is x squared. Outside terms is going to be xh. Inside terms, another xh. And the last terms would be an h squared. And I still have that minus 3x and that minus 3h off on the side. So as I prepare to distribute, I notice I have these 2 xh terms, so that's just going to be 2xh. So I'm going to distribute now. Give myself a little more space here. Distribute this 2. So I got 2x squareds. I got 2 sets of 2xh's, so that's going to be 4xh's. Then plus an h squared minus 3x and minus 3h. And overall, there's nothing else I can combine. I've got an x squared and no other x squareds, and xh, no other xh terms. I have an x and an h, but no xh terms. No other h squared terms, no other x or no other h. So on this one, we end up with this fairly long scenario, but that's what the answer is. We can't do anything else with it. That is what we end up with. And as I do that, I did see that I forgot to distribute that 2 through there, so it should have been plus 2h squared. Otherwise, when I got to the end of the video and I said, hey, if there's any mistakes in here, please go ahead and let me know. You would have said, hey, on that example with letter h, you forgot the 2 when you distributed. So glad I caught that in this particular piece. Okay. So what do? We just did a lot of substitutions as far as what can we do with a function rule. So our function rule in this case is what I have highlighted up here. Let me get rid of this highlight perhaps. So we had f of x equals 2x squared minus 3x, and then we did all kinds of things. We did 2, 4, 6, 8 different scenarios as far as what could we plug in for x, and how does that change each and every component. Okay? So that is things that we can do with functions. And the reason we can do these and they work is that, again, remember the idea of function. For every item that I plug in, I only get one item back. I get exactly one output for every input that I go ahead and plug in. Now, these functions can take different forms. We can have what's called implicit functions, and we can have explicit functions. So implicit functions are when it's implied that we have a function. So in other words, the ones on this left-hand side here, we could solve each of these for y and end up recognizing that for every input of x, I'm only going to get one particular y value back. The explicit form then is actually when we do solve for y and we see what those formats look like. Why do we have different forms? This left-hand side, we often end up with these as far as maybe the beginning format. We know some relationships that happen in some of the online calculators can go ahead and take things like, like Desmos will go ahead and take an input like that of an equation. Excuse me. Input of an equation, and then we can calculate. Other items as far as the explicit forms, these are traditionally what we need to plug into our calculators. So our calculators traditionally only have like a y1 equals or a y2 equals or a y3 equals, and we have to very specifically state in terms of y what we have, because in terms of y is also the function itself. So we have different types of things that we have. They can take different forms, different shapes, and that's fine if they take those different varieties to go along through there. Okay. We still have several more items left as far as our functions here far as things that I want to get through as far as this particular section. This video is already edging close to 55 minutes. So I'm going to go ahead and stop this video here. We're going to call this part 1, and then I'll do another video, part 2, and we'll wrap up section 3.1 on functions in another video.